Good evening, everybody. Can you hear me?
Yes.
Okay. So my name is Pradeep Balakrishnan. I'm VP of Engineering for a startup company called Formulas Black. We are based out in New Jersey, headquartered. We got a bunch of folks around the U.S. Who are working with us, and also we have a small team out in India. We are venture-backed, and our CEO is Mark. He's in the audience right now. He's an Oracle veteran himself. So what exactly are we doing? You know, we are like a software company primarily focused on building memory as storage. You know, how do we do that? So we call our software as Forcer. That is basically enabling memory that can be easily and also efficiently be used as high-performance storage media. You know, you would have heard about terms like RAM disk, you know, variety of things that you can do on DRAM and also NAND, but that's the first step. But then you got to make it more effective to make it as a high-performance storage media. So our goal is basically to use the power of the application, you know, tiers that can basically use memory as a storage backing device without having to change anything in the application. It's just, you need to just use it. And that way you're trying to minimize the latency and maximize the throughput and, you know, scale the performance, etc. So, you know, about my bio, I was a senior director technologist at Western Digital. It was SanDisk, a NAND team, before it became WD. And before that, I was with Seagate, doing a variety of things and also HPC stuff. That's about me. So I got a few questions over here. You know, what comes in your mind when you think memory? You know, using memory as storage. I want it to be interactive. So could you guys give some? Yes.
How do you make it persistent?
Very good question. What else comes to your mind?
Yeah, how do you make memory non-volatile?
Yeah, that's the same thing the other gentleman was talking about. Thank you.
And is it really fast?
Is it fast? Yes.
How costly it will be.
Yes. Very good. Okay.
One talk I attended said that when you really have very, very fast storage, a lot of the algorithms of the application above, like databases,
Mm-hmm.
are invalid for that kind of speed.
Yes.
Have you seen that, or?
Mm-hmm. So there are a few you know, things that actually pop up. One is the type of memory. You know, you got DRAMs, now you got Intel Optane 3D Crosspoint, what it's called, and then you got NAND-based memories, which are tier 2 memories, which is available, like IMDB technology from Intel, where you can actually use it as a hyperdrive using the SSD and giving the memory interfaces. So the physical aspect of that memory is there. So DRAMs, NVDIMMs, you know, DCPMM, all those words come into the mind, at least. And then we think it is like you got to have different memories, different clock speeds, different type of ASICs in them, whatever, you know, LRDIMMs, RDIMMs. It seems like very fluid, that data. People have to actually figure out what happens when a LRDIMM goes in or RDIMM goes in. What exactly is the clock speed ticking up and ticking down, etc. And then, of course, memory, once you say, like you said, speed, blazing speeds. You know, that's what people, you know, if you're a gamer, you want to run, you know, some good game on a RAM-backed device, you will absolutely love it. You know, you don't think, why do you need a GPU? If it will be fast. That's the other thing that actually comes in mind when you actually think about memory. And then, of course, you need to make it persistent, so you need to have some kind of battery backup or some kind of a thing that to make the data persistent, because it can be, you know, speed actually kills. They used to say that. So that's memory. If you lose power, it's all gone. So how do you make it more persistent? And of course, it is expensive. And with DRAM prices, some friends at Micron, if they are hearing it, they'll be pleased. You know, the prices might pick up, and Micron and SK Hynix, all our friends in Silicon Valley, will be actually looking at the prices to go up. So it is expensive. So we basically see all these factors when you think memory as a device. And we in Formless Black want to have that achieved by making memory as a storage media. So we are in memory compute, and we look at the physical medias, as I said, volatile versus persistency, the cost factor, and performance versus capacity. How much can you give in performance versus what is the capacity? And to the last point, what this gentleman was talking about was, what is my application tier, which is like the databases, what do they actually achieve? You know, what can be achieved, if I understand right? So you need to have, yeah.
So what is the reason for the prices to go up, or the number of players decreasing, or is there anything else happening in the industry?
Well, this is what I hear from, you know, like television channels like Bloomberg or whatever. They basically say the glut is come down, the memory glut has come down. There was a recent shutdown of factory operations of Western Digital in Toshiba, so the NAND supply will actually start to shrink, and they'll see that the market, the prices might tick up.
So the supply versus demand scenario.
Correct, yes, exactly. So basically, to achieve all these kind of things, you need to have hardware support, and it also needs to have some memory channel, and then most importantly, with memory interface. If you're aware with PMDK in open source, you know, like SPDKs, PMDKs, or liblite NVM, you know, we contribute a lot to that areas in open source. If you see those interfaces, there are a lot of memory interfaces coming out in open source, and you can see that. So you need a programming model as well to program these different type of memories. So what is the next change? Now you have come to the physical abstraction, the hardware. We just saw all the type of memories, the clock speeds, the different type of memories, you know, the application tier, volatile versus persistence, performance, cost, etc. These are all the system-wide physical attributes. Then comes the software. There's always a saying that software creates more problems than hardware, but we try to eliminate that. So we have to think about reconsidering the entire software stack. So the first thing is this interface model, which I was talking about. You need to have a very good persistence memory-based hardware, and the software should be able to adapt changing first. For example, programming models. IMDG is one example I said. PMDK, DAX. I don't know if you folks are aware of DAX. DAX is one other programming model. If you're into Micron DRAM stuff, you will be getting into DAX. And also multiple things which are related to the application tiers, which this gentleman was talking about, roughly, which is like you have the operational infrastructure services, basically Oracles, the SAPs, and all the business apps which are actually going to use these things. And then comes the Linux stack. You know, in a bare metal Linux, it's already getting complicated, that stack. If you look at the kernel picture today in Wikipedia, whatever, you can actually see the different type of interfaces, the buses, the drivers that go with it, the kernel, and then if you have NVMe, there is SPDK, which is the unkernel stuff, where you want to access the device, everything. So what we actually are seeing is all these different type of provisioning models for these type of memory devices is also a challenge. So once you have actually defined the memory as a storage element, how do you programmatically make it as a medium, which behaves like a SD device or a block device? You know, it's easier said than done, because you are now entering into an area where the device, the backing device, is not designed for like that, like an SSD. But now you're making RAM to work like a compute device, but behave more like an SSD or any second tier memory. So which means that you need to know the programming model for to make it persistent, the interfaces you've got to define, and that interfaces has to be accepted at the kernel level. So the kernel actually thinks it is a raw block device or a POSIX block device, etc. And then finally comes the, you know, this application tier. You have the database applications, RocksDB, you know, some caching techniques. You can do some optimizations for different type of bins. How do you actually accelerate certain type of RocksDB queries? Or if you have like local queries, how do you optimize them, etc. We have some use cases for those. And then what about the traditional software as well, which are not designed for memory? You know, if you look at RocksDB, those things are designed for in-memory. you know. Oracle has extensive things for in-memory. And so does some of the databases have taken advantage, but there are more legacy apps which will not change. They are not going to change. And what about those? How do you make them actually work? And finally, the Linux IO stack and all this kind of stuff is actually treating. You need to treat the block device as a raw block device in Linux stack. And then finally, you need to look at the virtualization. What if you have a KVM on top, or a container, you know, with Dockers or Kubernetes microservices running on top of it. So yeah, I'm just building the stack up. What I did was go from the physical abstraction of the memory, and then work up the software stack, which is the kernel, exposing it as a device, and then build it all the way up. Now your device, as a memory packed, all of a sudden looks like an SSD, but it is blazingly fast, and you can run execute workloads with QDEP as one. You don't need QDEP 32s or anything like that. It's blazingly fast. So basically, I just spoke about all this stuff. Now I'm going to actually talk about. So now, basically, so it looks like it is simple. You know, using memory as a storage media is not simple. That is exactly what we found out, and it has got way to go. So what you have to do is you got to use it correctly, and you got to be efficient with it because it's expensive media. The price per gigabyte on memory, backed by memory, is expensive, but so does the performance. You can reduce the CPUs, the number of CPUs, the physical sockets. So think about the number of CPUs instead of peripheral device. So here is a picture that we have, and I thank my colleague Ian to actually put out this pretty picture in New Jersey. So we got multiple CPUs over here. And if you're doing memory, you got to think about the CPUs. These are all these guys who are sitting idle. There's one guy who is doing a work, and all the other CPUs are basically watching him. What it means that is you got to make all the CPUs work for you. So today, if you see certain applications, what we have seen is they lock them to a one core or one socket, and they pin themselves to that, and they cannot be scaled. But the customer is basically thinking like, oh my God, it has to scale. How do you linear scale memory, which is attached always to your one physical socket, and never scale? So that's what it means. And second one is, you have to think about memory management. So when it is memory management, what it means is if you look at the far end picture, the memory links to the CPU and the I/O processing, everything should be streamlined. Memory is very disciplined bus. So what the picture says is it is very crumpled up, and you cannot have connections like that to the memory channel between the CPU and the memories. If your programming model is actually crisscrossed, you are going to end up with a lot of amplifications. It can be writes and the reads and whatnot. And then, so then last comes is it is the story about the time and space. So you got limited time because memories are very fast and so is CPU. And then you basically have to think about, you know, how do you achieve that? That is the most important thing. So memory, closest neighbor is the CPU. And they do talk very fast, but your peripheral devices are not fast, which is all on PCIe bus. So you induce more latency up. Now the effectiveness is how do you make the apps actually take advantage of this low latency stuff? Because there is file system in between, the file system has got its own latencies and caching techniques, whatever. So anyway, so then comes, I'm talking about, you know, that's what we try to solve with our software enforcer, which we can talk in detail later. And then what we realized was the hardware and, you know, software support. So being a software stack, what we did, we realized that if you actually bundle this into an appliance, some customers are reluctant. Some customers might think I don't need to manage another box in my data center. What if this software can actually be pluggable in a Red Hat kernel or a CentOS or Ubuntu, pick your favorite, or even Oracle Linux if you're into it, and install it on the fly, make memory as a device, and you mount your applications or file systems on it, and execute your workload. And all these back-end tasks about how a SAN works today, like, SAN has got technologies like it has a scrubbing engine, it looks at all the medias to see if the media goes away, the physical media, the logical extensions, drive replacements or disk replacements, etc. You've got to see from all perspectives when you design a SAN. But if you can actually make a commodity hardware, a regular Supermicro chassis or pick a chassis which you like, install Linux, install software, use memory as storage media, and then you mount it. And this storage media is different than from traditional RAM disk or something, where you actually make it behave like a real volume. And if that volume from one node can be stitched across or joined across nodes, thereby you're creating an artificial memory fabric, then you're exposing the memory of one node to the memory of another node, and your app actually thinks they are all traditional devices, block devices, or POSIX blocks, and they spread this I/O. Now across the fabric, you're actually striping the I/Os from node to node. Now the fabric is obviously the fastest today is InfiniBand, unless we had some other fabrics like ZBus or whatever. So that will take a while, but today it's all InfiniBand. That's how we have tried to solve the problem. And the next one is the operating system. Today you have like some are Debian fans, some are Red Hat fans. But if you walk into a data center, they're gonna basically say that I'm not gonna remove Red Hat. Can your software run on that? So we made it as like installable and uninstallable. So if you want to see the performance, what our software stack we designed using memory as a device, install it, execute your workload, uninstall it, no changes required, and then you just mount your regular app. You'll just see the tail latencies of the application go immediately different when you see memory as a device or a storage media. And then when you use a regular NVMe front-end SSDs with soft rate, whatever rates you like, or if you're into objects or whatever, you will immediately see the latencies go up because you need to have QDAP to those PCIe channels. With memory, you're using QDAP as a 1. That's it. And with the Intel Optane actually coming out, we are already working with them, and they make persistence happening. And then what we have done is not only increase the performance of it, but we have some unique technologies which we actually have. We can talk about it in later sessions. We call it as bit markers, where we amplify the capacity amplification of memory. So if your physical system is 6 terabyte, and you're carving out all these memories into logical volumes or SD devices, and you're mounting file systems, and you're using across multiple nodes to create a 6 terabyte volume across multiple nodes, and then you mount Oracle on top of it or MySQLs, what we actually do is we take this memory region and we scale it across all the physical CPU sockets. So that will be the first step. When you actually try to have a memory device and you want to scale it across 2 different sockets of CPU, you will see the challenge. NUMA architecture in CPU works different versus memory architecture. Memory likes to be attached to one device, one CPU socket, and you need to actually split it across the cores on the single socket. And then imagine you have a second physical socket where you have same virtual cores. And then you need to map them like a mesh. So if you know like VNAND or ZNAND technologies in NAND, you do this linear mapping with the x-axis and the imaginary axis. You got to stitch it. What we call it as the NURA architecture, which is the memory architecture with NUMA of CPU. So we kind of blended it both. So anyway, going back to this, so we basically support commodity hardware. It can be DRAM, it can be Intel Optanes, or it can be a blend of both. And then we work with any Linux distribution. We don't have any Windows support yet, but it's all Linux. So what are the deployment options? So the first question comes to mind is, okay, you have this fancy software, it can do voodoo magic. That's what many of my friends say. But it actually does some magic. It used to be something like that, but now it is actually doing it in customer sites. We have multiple POCs going on. It's blazingly fast. Luster is so fast on HPC workloads. we can share some of the application workloads that we have been doing with our partners Intel on some testings with Optane. So we call it as the host or bare metal mode. So we have an option where the app administrator says that I don't need any virtualization stuff, I don't need any containers, I need bare metal. I just need to load this file system, which is like Lustre or IBM GPFS or any other file system or application, and they need to get bare metal speed. And what we do with Fossa is to basically scale the RAM or the memory across all the physical CPU sockets, and then carve out volumes for that particular workload. And then using our fabric, NVMe or fabrics, we actually stitch it across. So in a bare metal scenario, if you're into a bare metal cloud provider or something, you just need to actually get our software, install it on the cloud instances. And then you actually amplify the memory usage as well. When I say amplify, it's not write amplification or anything, it's a capacity amplification. So your 6 terabyte will actually be, the actual usage of 6 terabyte will be like 3 terabytes or 2 terabytes. So we look at bitmarking technology where we actually do capacity amplification. So your physical memory will be 6 terabytes, but you end up using actually like 2 or 3 terabytes at the max. The remaining is always available. And then we also support virtualization mode. In this we have a blended mode with KVM, and also we support like Dockers, so which are all open source anyways. It's just you need to get it from certain repos and do it. But we did a tighter integration with instances. For example, like when you do clonings, when you do thin clones, fast clones, whatever clones you want to call it, when you want to do migration across multiple nodes, we usually do it from in RAM. In DRAM, when you actually do it, the way to do it is you do reprefetches again, multiple reprefetches, because you're actually ahead. You are actually ahead than the traditional NVMe SSDs. So your seeks, if you're a drive guy like me, your seeks will actually be nil. DDR guys will not even know what it means, but they know about read ahead and prefetch. So, and then in post metal, bare metal, what are the things that we are looking for? This is to answer your point. In bare metal mode, you actually can use very data intensive application. So what we do is we sit in the RAM bus and we actually utilize the CPU lockings for each of these NUMA regions or NUMA sockets, and we make memory as a big real-time memory. It's like a storage pool, you know. And then you carve out LUMs, we call it as LEM, logical extended memories, and then you mount your applications and then you start to pull it away. So these are all container virtual machines, same thing, and then can it scale? So we tested it for a single box with just DRAMs. We have some, I can share you some data sheets, or I can send it over emails if you want, on what the information is. And then we actually scale it across fabrics using NVMe or Fabric. We have some very good test results that we did with our partners at Intel. We are also working with some customers, POCs, where today they use very good all-flash arrays, and we just go in and take an old pizza box, which is a super micro running Broadwells, Haswells, Skylake, something, and we just fill up some memory DIMMs, load up our software, load good old Linux, and the guy just looks at it, and the front-end IOPS will be in 16 million. And they will be looking at what is this other extreme IO is doing. So there are use cases where we will use like a scratch partition for HPC workloads, a burst buffer, checkpointing, whatever words you want to call. So we do something called vertical scaling and horizontal scaling. So this is, we call it as the performance LEM. So I talked about LEM, which is like a single volume. Imagine you have two LEMs, you can either stripe them together, or you can actually do like LVM concatenation modes, where you write into the first LVAs and the second LVAs. But in memory, you got to do it a little different. So we have both type of models. So anyway, that is roughly what I got, where you use memory as a storage media, whether it can be DRAM, it can be NAND, or SRAM, whatever. So now I'm opening up to any questions you might have. Yeah.
Did you try to do caching to use the cache rather than just your storage media?
Yes, you can. So the reason why we wanted it as a storage media is because we created a storage pool. Where in a caching you got to either mount the write cache or read cache, you got to be very specific, and if it is write cache, you got to say write about or write through, etc. But if you are doing, like, for example, RocksDB or any other application like Ceph, you know, they use RocksDB in one area, and you can use one of our LEM as a cache device. So you can partition the memory into like little volumes, and you can mount your cache regions. Like RocksDB has got the pool filter cores, and you can actually mount those things as a caching region. For Ceph or any other app, you know, there's massive application tiers. They just see this memory and they think that it is another memory region, and they can use it as a cache. Except our software is actually doing pattern matching, and also something like AI. We actually look at patterns of data that comes in, and we do unique way of doing bit marking. So we don't write the full byte. So your throughputs will be fast. A 4K page write will not be 4K. It will be actually be much more than what you write in memory. But anyway, to answer your question, yeah, absolutely, you can use it as a cache as well. So in one of the HPC deployments, the customer is actually using it for burst buffer or scratch for IBM GPFS. So there we just create the region and leave it for the customer, and they have been using it ever since. Yes.
So because are there any self-diagnostic tools that's sitting in the software, because we have so many stacks involved, from application to edge computing to server to database to your memory?
Yes.
So would it give a check mark that it is working well on the software and hardware side when it comes to memory, so that debugging makes it easier on the other side?
Very good question. Actually, I didn't even go to that. So we have something called the central fault tolerance manager. So when your multi-node spread out across NVMe fabric, you need to do error finding on ECC checks. So we actually do that background scrubbing. We call it as a background scrubbing, and then we also have a technology called as the background bad block replacement page algorithm. So in memory, it's all pages. So we actually have a daemon that keeps on going around looking at all these nodes. And if there is a hardware fault, we make remediation of actually mirror copy the LEMs that are being affected to another region, just like drives do today in SAM or filers, except that this is in memory. That's what we solve. And we also alert through the traditional SMTPs, emails, and text to phones. All these kind of upper ecosystem notifications are also there. Okay, thanks everybody. Yeah, that's very best. I'm sorry. I didn't mean to make it.
Presenter is Sam Drake. He's an architect at Oracle Timestamp and Memory Database, and Sam will present about thinking about performance. As I mentioned earlier, if you guys register for the GridGain forums, you'll get 2 tickets to the In-Memory Computing Summit, free tickets. So I'm gonna distribute a short URL link that you can just type in and get directly to the registration page. Alright, the floor is yours.
Cool.
Yeah.
All right, thank you very much. Can everybody hear me okay, back in the back?
Now, yeah, I think it's off.
Can everybody hear me okay back in the back? Well, let's see. Seriously, is that about where it ought to be? Okay, all right, well, hi, my name is Sam Drake. I'm an architect in Oracle Times 10 in-memory database development. I've worked on Times 10 for, excuse me, more than 20 years. That's why I don't have any hair left. And so I'm gonna talk just for a few minutes about performance in general. Times 10's been presented at these meetups a lot. You know, Oracle's one of the sponsors of the series, and so I'm going to talk to you a little bit about Times 10, but mostly I'm going to talk to you tonight about kind of some basic things in how you should think about performance and how you measure performance and what aspects of performance might be important to you. How many of you are like performance gurus at your company? How many of you think all day long about performance? Well, you're in the wrong talk. So go have some more. Go have some more macaroni and cheese. It's really good. One of the things I've learned, you know, in trying to sell a performance-oriented product to people for more than 20 years, as Brittany Field discovered, is you know, a lot of people don't understand performance. They don't quite understand how to think about it. You know, they think fast good, slow bad, but I just wanted to take a couple of minutes here tonight to talk about performance in general. And of course we'll illustrate some examples from that with Times 10. But I'm not really here to talk to you about Times 10. I'm here to talk to you about performance at a higher level. This slide says basically everything I'm about to say is a lie. You know, I'm going to talk, to the extent I'm going to talk about Times 10 tonight, I'm going to talk about a product we've been selling for 20 years. There's nothing, I'm not pre-announcing anything new here tonight, but if I did happen to say something about a feature in Times 10, and Times 10 doesn't have it, I was just lying, I guess, or something. So don't make your buying decisions based on anything I say tonight. I went too far. I'm gonna figure all this out. Okay, so everything I say is a lie. So how many of you are using Times 10 today? Right, that's the normal answer. It's not actually the answer, because Times 10 is used under the covers in a lot of things that you use every day. Although probably none of you use it know about that. You know, Times 10 is used to run more than 1 billion cell phones around the world. Times 10, if you've gone to the grocery store and bought a cart, you know, for some sort of prepaid, you know, $200 worth of something from company X, and then you slowly spend that off. We probably hold the balance for those cards, right? If you've ever mailed a letter, you know, we've been involved in checking the stamp on that letter to see if that letter is good, right? So none of you are probably Times 10 customers, but every one of you has used Times 10. So since I work for Times 10 and I'm here, I do have to tell you a little bit about what it is. Times 10 is a pure in-memory database. It's one of the first pure in-memory databases. Was started as a research project in 1994 at HP Labs. Was commercialized starting in 1996, and is still you know, being sold and developed today. It's a pure relational database. SQL, rows, columns, tables, select, insert, update, PL/SQL stored procedures, standard data types, just like any other SQL database on the market. Looks exactly from the outside exactly like a standard database that supports JDBC and ODBC and SQL and transactions and all the stuff that any other relational database would. But just happens to store all that data in DRAM. Under the covers, so you don't have to think about how hard that is. Times 10 databases are persistent and recoverable. Naturally, when you think about storing data in memory, everybody says, well, but it's not persistent. That's true, it's not. But Times 10 databases are. We still use traditional block storage, disks, flash, etc. to write checkpoint files and logs. Every time data is changed, those changes are still written to stable storage. In addition, they can be replicated to other systems under the covers. So an in-memory database is persistent, can be persistent, ours certainly is. As an example of that, the two industries that use times 10 the most historically, one of them is telecom. Like I say, we do run more than 1 billion cell phones around the world. If you think of all the text messages and phone calls that are made per second in China, it's not an exaggeration to say that we do all the billing for all of those in real time, right? So how many texts are sent in China every second? That's a lot, right? And so that's a lot of volume. But the other industry that uses times 10 very heavily is financial services. Think of stock trading, right? And in that world, the difference between those two worlds is, if I forget to bill for a text message, so what, right? It's 1/10 of a cent or something. But in Wall Street, you can't lose anything, right? Those transactions are worth millions of dollars each. And times 10 fits equally well into both of those worlds. So times 10 databases are completely persistent, full stop. Because it's an in-memory design, the times 10 is very, very fast. We'll talk more about that as we go through the presentation, but we measure response times in microseconds, single-digit microseconds. If you want to use a standard select from a standard application through a standard API, just like you would to 20 other databases without changing a single line of code, 5 milliseconds, or 5 microseconds, 5 millionths of a second sort of response times we can provide, along with very high throughput. And kind of going along with persistence and recoverability is high availability. As I said, we can store multiple copies of your data. We can store multiple copies of your data in different data centers and different geographies. We can, in some configurations, provide K-safety, so we'll automatically store 2 copies or 3 copies or 4 copies of all your data. So if anything goes down, your data is still around. So that's kind of what times 10 is at a high level. Now, so any questions about that before we go on? I'll just throw it out here. Yes, sir?
No, what is K-safety?
K-safety just means that in a distributed database, think of things like Cassandra, you can define how many copies of a particular piece of data you want the system to store. So if K is equal to 3, then 3 copies of each row are kept in 3 independent systems. That's really all that means.
Thanks.
Like HDFS, right?
Yeah, I guess. I'm not familiar with their use of the term, but think of K safety meaning that we store K copies of all your data in independent places. Okay. So as I said, times 10 is used around the world. I think I already gave the sound bites, right? More than 1 billion cell phones, used all over the place in things that are mission critical and lots of people use every day. But it's a niche thing, right? Not, if anybody had stood up here today and raised their hand and said, yeah, we use times 10, I'd be kind of astonished, right? But all of you have used it, I promise. Okay, so that's the introduction about times 10. Now we'll talk about what I was going to talk about tonight. And this is kind of a standard slide. It sort of says, everybody who comes to an in-memory conference says, boy, there's a lot of memory these days, and we got to figure out something to do with it, because Micron and Intel and those guys can crank it out, but what in the world are we going to do with it, right? And for folks like me, I remember the days, when I joined times 10, right, our servers had, 128 megabytes of RAM and 2 gigabytes or 4 gigabytes of disk, right? And now 10 years ago we were being deployed on systems with a terabyte of RAM, right? And today, and that was a leading edge thing, but you can just go to any of a dozen websites, and if you want to buy a server with a terabyte of RAM on it, just click the button and they'll mail it to you. It's not a big deal anymore, right? So there's RAM everywhere, and what in the world do you do with it? And everybody's coming up with innovative things to do with it, which is great. Because there's all that RAM around, systems are faster than ever before. And if you're interested in in-memory computing, presumably that means you're interested in fast computing. But what fast means is different for different people, right? And I'm just going to start with what is probably basic, and I apologize if it is. But you know, there is, to me, when somebody says I need a fast computer or I need my system to run fast, that doesn't mean anything, right? And we can break that down into a couple of different categories. The first set of categories I want to talk about are just the difference between throughput and response time, right? You know, when you think about the throughput of a system, and you say I want a fast system, maybe what you mean is I need to handle 10 million requests per second through my system, right? That's throughput. How many requests per second can your system, can your application handle? But a different way to think about performance is response time, right? You know, I'm not interested in sending 10 million requests through the system. Maybe I am sending 10 million requests through the system, but for just one of those requests, from the time it's sent in to the time the response comes back, how long did that take, right? That's response time. That's how long that individual application or user had to wait, right? So two completely different, they're kind of related, and we'll see, as we'll see, and you probably already know. But throughput and response time are two really different ways to think about performance. And so just, you know, please don't just say you want a really fast system. Please think about whether you want your system to handle a whole bunch of requests or to handle each request really quickly, right? Because the way you design your system, your application for those can be very, very different. And the way you deploy them can be very, very different. Question from the gallery over there.
I mean, are these two really different?
Yes.
One is the inverse of the other. So.
No, and the comment was one is the inverse of the other, and they're not. They kind of are, but they're not. I have a slide on that in just a minute. But they're, I mean, for example, and just to put a simple thing on it, if you had one CPU and you could only do one thing at a time, then they're inverse, right? Then if you did 1,000 things per second, then each thing took 1,000th of a second. But if you have two CPUs, they're not inverse anymore, right? Because you can handle two things at once. And so if you're doing 1,000 requests per second, then each one could take 2,000ths of a second, 2 1,000ths of a second. So they're not exactly inverse, but we'll talk about that more. But thank you for making the comment. Okay, so at a really high level, when you're thinking about performance, I need a high performance solution, or when your non-technical boss comes to you and says, you need to speed this thing up, right? First question you ask him should be, you know, in which way, right? Because they are not interchangeable. And here's an example of that. Now we're going to talk about the relationship between throughput and response time. And they are related, and they're related in a way you won't like. Meaning that increasing your throughput will also increase your response time. Take a look at this graph, and this is not a real graph. I drew this in Excel, but and it's not from times 10. It's about every single software product ever built, right? If you suppose you vary the number of, suppose you've got your system deployed, and you send in a workload to it of 100 requests per second, right? And you measured and you checked to see that it could handle those 100 requests per second, and you measured the response time each request was getting, right? So you've got a value for throughput and a value for response time. And then you double that workload. You send in 200 per second, and 300, and 400, and 500, and 600, right? So what you'll see, let's look at the blue curve, which is throughput, right? The throughput of your system is going to go up. You know, if you say, okay, I'll do 500, okay, I'll do 600. And then you're going to hit a point where the system can't really do it anymore, right? And it's going to kind of top off. And then if you keep trying to overload it, you say, well, I know you're having trouble doing 10,000 requests per second, but here, try to do 20,000. Performance is going to go down, right? Every piece of software ever written will show that curve, right? You know, there's no axes on here, but every computer system ever built will behave like that, right? It performs really well until it can't get any bigger anymore, and then it'll fall apart. That's the way the world works. Okay, so what happens to response time at that same time, right? Well, when the system's really lightly loaded, no big deal. You'll get good response time, right? And even during this phase where, again, the system's trivially able to handle the increased workload you give it, no big deal. It still can generate more or less, crank out more or less that same response time. But then you'll get to a point where the response time starts to go up. And the reason that'll happen is because you're getting queues, right? Suppose you have two CPUs, right? All of a sudden and usually when a request came in, one of the two CPUs was idle, and so the system could start working on your request right away. Well, as soon as you've got both CPUs busy handling requests and a third request comes in, then that third request has to wait a little while, right? It gets queued up. And that's okay, but the response time that that third query saw, that third transaction saw, is going to be longer, right? So you're going to get to a point where you start to queue up requests, and your response time starts to get bad. And then and it'll get worse and worse and worse and worse and worse, and then eventually it can't get any worse, and that's kind of the way it goes. And every system ever built will have that response time curve too. This is just, I'm not talking about science, I'm not talking about engineering, I'm talking about physics. This is the way computers work. So I guess my first message to you, just, again, I apologize if everybody knows this, but look at the curve a little more carefully, right? Suppose you want to run your system in the best possible way. Well, what does that mean? The best response time is here, right? Here's where you could run, a whole bunch of transactions per second and still get basically the best response time ever. But the place where you got the most throughput is here, and your response time has started to degrade, right? So again, when your pointy-haired boss comes in your office and says, "I need the system to run faster," the first thing you ask him has to be, "Do you want more throughput or do you want faster response time? Which do you want?" Because you can't tune the system to get the best value of both of them at the same time, usually. Okay, so that's again an example of how throughput and response time are different, and the corollary of all of this, I think, is when you measure the performance of your system, always measure your response time at a particular throughput. Artificially send in 1,000 requests per second and see what the response time is. Don't just plug it into the network and send in as much workload as it can handle and see what happens. You're going to be measuring some point out here where the throughput's awful and the response time's worse. And hopefully that's not the real world, right? You need to see what this curve looks like so you can pick where on that curve you want to move, right? So just ways to think about how you measure the performance of your system.
So in that graph what you have, I had a question. Is this local latency or over the fabric? Response time.
I typed some numbers into Excel to make that curve look the way I wanted it to look. I assert that this is the way every computer ever built works. I think we're just talking about mathematics, not any particular implementation. But maybe I'm wrong. If your secret sauce generates curves that don't fit this general model, you're going to take over the world. Okay. The other way to think about throughput and response time is from a business perspective, right? Tell your boss, well, which of those is more important to you, right? Improving response time is either irrelevant or vital, And for most people, it's kind of irrelevant. If you've got an application where somebody's sitting in front of a terminal typing in data, and if you don't need to provide microsecond response time when the user presses enter, it doesn't matter, right? Humans, quarter of a second or a tenth of a second or a half of a second, that's good enough for humans. But if you're doing program stock trading, and the price of Oracle goes up and you decide whether to buy or sell, you have to respond to that as fast as you can, because if the other guy responds a microsecond faster, he makes a lot of money and you don't, right? So there are environments where improving response time doesn't matter at all, and there are environments where the only thing that matters is how fast the response time is. And you can have to spend as much money as possible in order to get the best response time. But that depends on your business and what you're doing. And the same applies for improving throughput, right? If your website's only gonna get 200 clicks per second, there's no reason to build it out so it can handle 200,000 clicks per second. So what, right? So there's a business side to this too. You have to know what you really care about. And that's the thing your pointy-haired boss can tell you. Now to bring this back to times 10, because I have to tell my boss I did. You know, times 10, for example, can be deployed in two different ways. What we call times 10 classic and times 10 scale out. Times 10 classic is the product we've sold for 22 years, 23 years. It's a database that runs on a single node and can be replicated to other nodes. But the database size in a times 10 database is limited by the RAM on one box. And that's limiting. You know, it'd be nice if you could have an infinitely sized in-memory database. But by limiting it to one single box, that reduces a whole bunch of overheads. You don't have to have as much communication traffic, right? Networks are slow, even magical fabrics are slow. And so this is the configuration that gives you the best response time, right? If you want to execute a SQL select in 5 microseconds, this is the way you configure the software to do it. On the other hand, if you want a bigger database that spans across 100 machines, we can do that too. And that's a configuration called times 10 scale out. But naturally, and then the size of the database is can be anything. But of course, there's more communication overhead. And so the response times aren't as good here, but throughput is unlimited, right? We can literally do hundreds of millions of transactions against a single database. So, so again, you really, maybe I'm banging on this point too much, but throughput versus response time, you really have to think about which of those you care about and why. So the next thing I wanted to mention is concurrency, and this is why they're not the inverse, right? Because the way I think about concurrency is it's how many requests can be worked on simultaneously, right? If you had only one CPU and you were doing nothing but synchronous I/O and everything was single-threaded, then, as we said earlier, you'd handle one request at a time. And so if you got 1,000 requests in, you'd handle them one at a time in order, and your throughput would be your response time would be the inverse of your throughput. But real computers have multiple CPUs; they can do multiple things at the same time. And if you do I/O, right? If you try to read from disk or flash, those are asynchronous operations. So while your program is off reading from disk, the CPU can be doing something else for somebody else. And then finally, there are issues inside of how software is designed. How you do your mutexes and locking inside of your application, right? And if two threads in your application try to touch the same data, does that get serialized? Does one of them have to wait? And in most applications, one of them has to wait. So all of these things control the concurrency that you get. Now, and for those of you who are performance gurus, this may be the only interesting slide in this presentation. He's agreeing with me, so that's a bad sign. In-memory computing inherently reduces concurrency, reduces it, right? If you have a system that was built 30 years ago, right, a database or something, right? Every request, you're going to get a request in, you're going to use the CPU a little bit, and then you're going to have to go read something from disk. And then you're going to wait for a while you do the read from disk. And while you are reading that thing from disk, you can go handle somebody else's request, right? So in traditional computing, you have all this I/O going on all the time. And so if you had a 2 CPU box, how many concurrent requests can you work on at once in a system like that? Dozens, right? Because you're going to work on one request for a little bit, then it's going to do an I/O, and you'll put it aside, and then but the I/O is still working in progress for that one, so you're working on that request, right? So, so people are used to thinking about having thread pools and connection pools and number of worker processes. If you got a 2 CPU box, people will easily just trivially just say, well, I'm going to start up 20 workers. I'm going to start up 20 copies of my application. Well, and that's fine, or was fine, in old-fashioned disk-y style computing. Memory doesn't work that way. RAM is synchronous, right? If I do a load from RAM, that's synchronous. I don't get to do something else while that load happens. The CPU sits there and waits. So it's super duper fast, but it's synchronous instead of asynchronous. So if you've got 2 CPUs and a fully in-memory solution, how many requests can you handle at once? 2. Not 20, not 10, not 50, 2. Right? And so when people move their database from a disk-based database to an in-memory database, sometimes they'll just do that, and they'll just think, well, that was great, everything's going to magically work fast, but you've got to tune a whole bunch of other things. And the concurrency of your system is going to go down, which means that some of the values you're going to tune for connection pools and thread pools and things like that are going to go down to make your performance go up. Question at the back,
So
yes, sir?
your assumption though is that you're working in a lock-based system, right? That's
Yeah.
why you're saying it's synchronous and that, because you have all this mutual exclusion going on, you have lots and lots of concurrency, right?
I'm just saying loads and stores to and from RAM are synchronous.
But if you go into like a persistent memory, there's other models that are based on immutable versions, right? And so when you do a write to like cross-point memory, for example, it's a persistent write.
I know.
So there are other models that don't have that same characteristics that you're talking about.
And again, we're doing a 30-minute introductory talk, not a PhD thesis. So sure, everything I say may be wrong, but in general, if in general I/O is asynchronous, memory is synchronous, and there are some impacts of that into how you design, into how you configure and tune your application. Okay.
Except the 3D crosspoint is NAND.
No, it's not.
It's
3 cross-point.
Octane, you're talking about Intel Octane.
Octane PCI, it's not NAND.
It's not.
It's byte addressable. NAND is 16K.
Yeah, so you can buy that with the memory interface. It's not like it's like diode, right? You can talk to it.
I want to make sure I don't eat up Greg's time because he'll be mad at me. So I'll buy you guys a beer and we can talk about it in the back while Greg's talking to everybody else. Okay. The other thing I wanted to say about concurrency, and then I think I'm going to skip my last couple of slides, just for time. Lots of in-memory software doesn't have good concurrency. We've been working for almost 25 years, and on our in-memory database. And the two things that change the most, one is how big it has to be, from hundreds of megabytes up to terabytes now. And the other is how much concurrency we need. It used to be you could just lock the whole database and have serialize every request because people just had 1 CPU machines anyway. Now machines have hundreds of cores or hundreds of hardware threads, and you've got to have locks everywhere. You've got to have lots of mutexes, and you've got to have a lot of concurrency. The one thing, I guess, the warning I'd give you, if you're evaluating some in-memory software, and the first thing the vendor says is, well, how big is your server? Oh, you've got 32 CPUs. Well, then why don't you go run 16 copies of the app? It means their internal design doesn't have any concurrency, right? Good in-memory software should be able to run on as many cores as you give it, without you having to partition your data into 16 chunks, and give a 16th of it to 16 instances of their application just because they haven't got concurrency worked out correctly. So that's kind of a red flag for you to look at as you're evaluating in-memory software. And as the previous speaker said, think about horizontal and vertical scaling. Horizontal being distributing your workload across a lot of hosts. There are a lot of overheads in that, but it's great. And vertical scaling, you want to be able to scale, use big servers instead of small servers, and that's harder in a lot of ways. So choose software that can do both, like in the interest of time, just to be done in 30 minutes, I kind of think I'm gonna stop there. I had a couple of other little things I was gonna rant about, but I think I've probably bored you long enough. Any questions about any of this? Or about times 10 or about anything else? Okay, well, thank you very much. I'll be around, and seriously, let's chat at the back. So thank you very much.
Thank you, Sam.
Sure.
All right, our next speaker is from GridGain, Greg Stachnick. All right, he's the Director of Product Management at GridGain, and Greg is gonna tell us about cloud deployment best practices. And just as a reminder, right after this presentation, we're gonna do the raffle. Tonight's raffle is all about this famous Netflix show, Stranger Things. So we're gonna have 4 people that are gonna go home with 4 different prizes. We have action figures, we have a Polaroid camera, so make sure to register. The tablets are at the back of the room over there on the bar. We still have some food left, so thank you GridGain and Oracle for sponsoring tonight's meetup. The food is amazing, so make sure to refill your plates and let's
Thank you
cheer
to
for Greg.
Tatiana for doing all the work.
Yeah.
Hey everyone, can you hear me okay? So my name is Greg Stachnick. I'm a product manager at GridGain and also I work on Ignite. And I work on basically our tools as well as kind of cloud strategy. And so what we'll be talking about today is basically some best practices that we've gained by basically taking Ignite and GridGain and supporting customers that both want to containerize their applications and deploy them into both public and on-premise kind of cloud architectures. So the agenda, I'm just going to kind of define some terms because when we talk about cloud, it can be kind of an overloaded concept. We use a lot of different vocabulary, and depending on our background, we may interpret it to mean different things. We'll talk about where people deploy applications or in-memory data grids into different clouds and what the options are and kind of the pluses and minuses. And then we'll get into some best practices. So for those who, just a quick show of hands, how many here are familiar with Ignite or GridGain? Okay, so about half, that's great. So for those that aren't familiar, so GridGain is a memory-centric data platform that's used to build fast and scalable, resilient solutions. And it's equally good at adding speed and scale to both new and existing applications. And it's built on Apache Ignite. So Apache Ignite is, I believe it's the 4th most active project in Apache. And GridGain provides the majority of the support, coding, and bug fixes and everything like that. So with a distributed memory system like Ignite and GridGain, some of the use cases that people often will look at are things like distributed memory-centric storage. So being able to take massive data sets and load them into memory by distributing them across multiple nodes. They'll look at things like co-located compute. So if you're distributing your memory or your data across multiple nodes, if you put the compute operations in the same location as the data, things go a lot faster. You save on network latency, disk latency, things like that. let's see, Ignite also supports, and GridGain support multiple ways to work with the data, both via distributed SQL as well as key value. It supports ACID transactions, and as people are building their clients to work with the data, we support multiple languages. So you could build clients that are based on Java, C++, .NET, PHP, and you can expose your data as REST endpoints as well. And some of the customers or some of the industries that tend to use Ignite and GridGain, a lot of financial services, real-time analytics, even airline industry, machine learning, all those kinds of things. Anything where you're having to do massive, get lots of speed on massive data sets. So a few years ago, I should say, well, GridGain and Ignite have been around for at least 5 years. And in the original set of customers, we're often using it on premise in kind of traditional bare metal deployments. But over the last couple of years, maybe 3 years, we've been seeing more and more customers want to kind of change their architecture and take advantage of new technologies. So things like containerization or being able to deploy their grids into both on-premise and hosted clouds. And so for us, in order to support those customers, we had to take a hard look at our architecture. And we did a big re-architecture a couple of years ago. And with that, we also joined Cloud Native Computing Foundation and Linux Foundation, just to make sure that we're supporting standards and that any customers that want to run in these configurations can, we can really support them to do like cloud native or cloud first based deployments. So what is a cloud? Oh, is there a cloud? No, okay. So what is a cloud? Well, it's a really overloaded term, right? You can ask anyone outside anywhere and they'll tell you it's where my photos get stored when I take a picture. Or it's where my text messages go. Or if I'm, working in an office, maybe it's where I collaborate on Google Docs or Office 365 PowerPoint presentations. Or maybe I work in a business that's doing sales and marketing and I need it to do some BI against a sales campaign or a marketing campaign. Or maybe I'm a developer that's building a custom application and it's where I run those applications. So vocabulary can be very overloaded. I mean, even like GoDaddy and Wix call themselves cloud companies when just a few years ago we called that web hosting. And so I looked at a couple of different vendors that call themselves cloud companies that we all will agree are cloud companies. But the way they describe the value of cloud is very different. And it really depends on kind of how you're using a cloud. So if we look at Salesforce, they talk about how they support flexibility, or they help you reduce your capital expenditure, or they are good at collaboration between teams, or controlling your documents, or I'm not actually remember how they describe environmental friendliness with using Salesforce, but that was something else that we found in their lists. And that really describe these kinds of value statements are kind of describe the interaction that you have with that product, right? Salesforce is a SaaS application. You're working with it as just a completed product for your sales and marketing and things like that. You can contrast that with like an IBM or Red Hat OpenShift. What are the values they talk about with the cloud? Well, it's about scalability, it's about storage, it's about security, it's about flexible payment structures, things like that. And that's really working toward customers that are wanting to build bespoke applications and looking for a more cost-effective way to deploy those things. And so there's a few terms that I want to just kind of establish as categories for things that we think are important for clouds, particularly for in-memory data grids. One is scalability. So one thing to think about is, if you're using a public cloud, this is not your infrastructure. If we think about how we would traditionally build out scalability in an on-premise world, we want to be able to scale. We need to buy hardware. We need to install software on that hardware. We need to hire people to maintain those systems. We need to patch it. We need to make sure it's secure. But if we're working in a public cloud, all of those concerns kind of melt away, right? Because we're paying someone else to do that for us. And so one of the values of working with public clouds is this ability to add capacity as needed. And that's basically scalability. That's why I put these rubber bands here. So the idea is that without having to purchase tons of hardware and hire IT staff, I can expand my capacity as needed. And we see this often even in our existing Ignite and GridGain customers. Some credit card companies will come around Black Friday, Cyber Monday, Prime Week, and see an explosion of credit card transactions, and they need to be able to scale immediately in order to support that without taking down their systems. And being able to deploy in a public cloud gives you those kinds of options. So scalability is one. Another is flexibility. So, and there's a lot of ways that we can talk about flexibility. One is flexibility as to where we deploy. So you may originally start with one data center, but you may need to migrate or make your service available in other zones to support different customers and be performant. Some customers that we see using Ignite and GridGain, the countries where they are running their applications have requirements that the customer data has to stay within the borders of their country. And so instead of building brand new data centers in every country of the world that these companies want to work in, they're able to use public clouds in order to achieve that. It also is nice because it gives us the flexibility of defining different machine specs. So different workloads may have, of a memory data grid, may require more compute. Others might be more memory centric, and so we can easily switch between different machine types in order for our applications to work. And then lastly, it makes it easier for software upgrade, right? So if I'm having the flexibility of being able to define images or a new release, I can take things down and then respin them up to put out new versions. But obviously, one thing to remember is that when we're working with these, this is actually not our data center, so some of the conveniences that we are used to when working on-prem are just not available to us, right? We are giving up some control by working with public clouds. And so some of the things we need to think about then, instead of SSHing directly into a machine, restarting a server, is the tooling that's available to us when we're working with public clouds. Another thing to think about also is all your data always hosted in your public cloud, or are you doing a mixture where some of your data is on-prem and some is in a public cloud, and how do you kind of rectify that? How do you work in a hybrid mode? So based on some of these kind of categories, we've kind of developed a set of best practices. And so one is around tooling. So when you have full control over your hardware, you can be lazy, right? You can SSH in, you can go into a data center, you can restart things, you can pull things apart, rebuild them. But if I'm working in a public cloud environment, I have less control. So the tools that we select can help us still maintain a lot of control and consistency when we're deploying data grids across in these environments. So one, if we're working in VMs or more of a bare metal deployment, automation is really important. And so configuration management tools like Chef, Puppet, or Ansible can make it a lot better for us when we're defining what is installed or how an individual node in our cluster is configured. Another thing to think about in terms of tools is how are we monitoring our grids? So how do we know if the amount of CPU that we allocated is running out, or if we're running out of memory, or if a node goes down and we need to recover from it, we need to take snapshots and backup. Well, the different cloud vendors provide tools natively. There are third-party tools as well that we can use. And then the in-memory data grid companies like GridGain, like Ignite, like Hazelcast, all provide their own set of tools as well. So from Amazon, you might use something like CloudWatch, or Azure. You might use Azure Monitor for more kind of coarse-grained monitoring of your instances. Or you may use something that's a little bit more generic that you can work across multiple cloud vendors, like a Elasticsearch or like a Prometheus. You may want to use tools to analyze the running applications to make sure that your grid is performing properly through things like AppDynamics or New Relic. Or, you know, if you just wanted to get a very grid-specific monitoring, you can use the tools that come directly from the vendors. So GridGain has a product called Web Console. It also has a product called Visor that can analyze the data as it's being stored in the grid. It can check for node health. It can check for things like replication of data across nodes and do rebalancing. But there's some other big tools. You could call them tools. You could call them just kind of deployment architectures or different technologies that are also really important, particularly when we're working with distributed systems, and that's containers. So Docker is the pretty much de facto standard now, I would say, when working with container technologies. So it's our standard unit of code that packages up our application as dependencies. GridGain and Ignite work really well in Docker-based deployments. So as I'm building up my nodes in my server, populating my caches, I can define them as containers, and then use a number of different ways to manage those containers. One of them being Kubernetes. So Kubernetes is just a way of managing those containerized applications. And so for memory computing, you can deploy your grid along with the rest of the application resources and allow Kubernetes to do the management of all of those environments. And then depending on the vendor, they may expose additional operation control to Kubernetes. From a GridGain or Ignite perspective, it's still a little coarse-grained. It's more for the individual nodes in a cluster. It's more kind of start, stop, restart. But we are looking to add additional kind of operator APIs to Kubernetes so that you can do more advanced management directly from Kubernetes, as opposed to using the control plane that's inherent in Igniting GridGain. Another benefit of using tools like Kubernetes is that if I am deploying to one cloud vendor, if I'm coding just against like kind of the standards of containerization, I'm a little more vendor agnostic as to where I'm deploying my application. If my in-memory data grid is just Docker containers controlled with Kubernetes, then I'm not necessarily making hard dependencies on AWS APIs, Azure APIs, Google Cloud APIs. So then I have a flexibility of migrating my application to different vendors or even doing a multi-vendor deployment. So I would be remiss if I didn't mention that we have our own kind of cloud deployment. I won't spend too much time on it, but it's called GridGain Cloud. It's basically a hosted solution for your caches and your nodes. It has the attached web console so you can monitor progress, and it's available across multiple data centers. It's currently hosted on AWS, and we're always looking to improve it and make it available in other cloud vendors as well. Most likely, you're going to be using one of the major cloud vendors, something like Amazon, to deploy your in-memory data grids, if you're running in a public cloud. If you're running on-prem, you might be using Cloud Foundry or OpenShift or something like that. So with AWS, there's a lot of options. And it's sometimes confusing navigating the list of like kind of top-level services in Amazon to know which options are the best. And so the next set of best practices are, I'll point out some individual kind of configurations and properties both in Azure and Amazon that we have found have been good when working with distributed systems. With Amazon, you're really making a choice between kind of 3 different deployment models. If you're doing kind of more VM or bare metal based deployments, then you're probably using something like an EC2. If you're deploying a container, like a Docker container, you have a choice. You can use ECS, which is kind of maybe their older container management system, or their hosted Kubernetes, which I think probably most people will these days because Kubernetes has become such a standard. The way that these instances are allocated to you, you have many options there as well. You may have an on-demand instance, you may reserve the instance, you may get a spot instance, and we'll talk about that actually in some of the other best practices, because there are implications as to how it's deployed and whether you're like sharing resources with other tenants. And then there's many different configurations for the instances themselves, the CPU and memory. So it can be a tricky kind of matrix to navigate to figure out which ones are the best when you're working with a distributed set of nodes. Azure's a little less confusing, or well, it's the same set of options, but they just package it up a little bit easier. So you kind of make a decision how you're doing your deployment, and then they expose more options as you're kind of going down either the VM route or the container route. So the next best practice is memory sizing. So the main thing we're working with in memory systems is which memory options will work best for the application that we're developing. It's usually easier to define our recommendations based around memory usage as opposed to CPU usage, but it really depends on the application. Is it more of a compute-centric calculation that you're running, or are you trying to just get as much data into memory as possible for scale? So one thing to think about is resilience when you're selecting memory options. So instead of choosing one giant memory module for your application, in-memory data grids often work best when you're using more nodes. So you can get away with getting smaller memory sizes. And one reason for that is resilience. So I'm taking my data and just spreading it across nodes in a cluster. And if I'm using resilience features of Ignite or GridGain, it's taking that data and taking copies of that data and spreading it across the nodes, so that if a node goes down, I don't have data loss. That data is still being distributed across other nodes in the cluster. And then the Ignite and GridGain can then rebalance the data across the remaining nodes while we wait for either the original node to come back up or where we add more nodes to the cluster. So in terms of like individual recommendations for AWS, we found that customers have been successful with 5R or R5D. R5D is better when you're using native persistence for your nodes. X1 and Z1 also work pretty well. They're probably big enough. We probably don't see as many customers using high memory. Was there a question?
Yeah, is the resilience happening automatically or needs to be configured in GridGain?
It happens automatically, but then you can configure how much is copied across individual nodes. So there's a default set of configurations, and then you can override it and change how resilience is controlled. So the high memory options, which are like 6 and 9 and like 12 terabytes of memory, is probably more than you need for a distributed grid. I mean, you can get away with like 256 gigabyte nodes across your cluster. Azure, we tend to recommend that people use the E instances like E32 or E64. We've also seen the G series can perform pretty well. With Google, the high memory machine types like N1 Hyman 64, which is like 400 gigabytes with 64 processors, that's plenty. That's probably too much. On the Oracle side, I used to work at Oracle, so I know a little bit about that. I would go with the Oracle Cloud Infrastructure, OCI, and I would go with bare metal instances. The other ones probably don't have enough memory. So that was a lot of different recommendations I have. We will publish the slides because I don't have them all in like a table here. And if you're confused, Ignite actually has a sizing calculator. You just enter in some details about the application you're going to deploy, and it'll spit out recommendations for you. For storage, if you're using storage is optional. You can be purely in memory. If you're using Ignite as an in-memory database, then storage is required. But generally, we recommend that people use the SSDs as opposed to block storage because of speed. If you're spending all of this investment to have speed and scale for your applications, why would you want to introduce bottlenecks for disk I/O with traditional EBS? EBS can be useful though for logging and things like that. But we would say generally, if you are using Ignite as an in-memory database, kind of stick with more of the SSDs. And that holds true. We found that works best both in Amazon and in Azure. And also, if you're using Kubernetes to deploy your applications, use stateful sets. That's kind of their version of how you do persistence. Images. So being able to have repeatable units when you're deploying your caches or setting up your nodes is very important. You don't want to be provisioning a VM or provisioning a container and then manually going in and making any changes, because nodes are coming up and down rapidly, and you want it to be as automated as possible. So for the VM-based deployments, you can create custom images using multiple different VM technologies. The individual cloud vendors have their own solutions as well, like Amazon and Azure. We tend to see more and more of the users just using containers. And there's even some default containers available off of Docker Hub for Ignite to get you started, just if you're not sure how to get started with an Ignite-based container. It also makes it easier to upgrade, because I can just take down an instance and send out the next version of my containers and roll those out in like a Blue-Green deployment or something like that. In terms of performance, when we're deploying to a public cloud, your application could be deployed on a shared resource, which is usually not what you want. You're at risk of having like a noisy neighbor that could be consuming more resources when you think that you have a lot more than you actually have. So in those kinds of things, you might want to go with like a reserved VM, where you define the time that you have access to those instances. Spot instances also work, but we generally think that they're better for bursting. So if all of a sudden you need to expand your capacity immediately, then we recommend using those spot instances. Kubernetes, we recommend using the horizontal pod autoscaler to improve performance. And then there's also auto scaling just built into the cloud providers. EC2, Azure, as well as ECS have rules that you can define based on resource consumption. You can have it spin up additional instances. So for security, it's important, because when we're working in a distributed, one thing to think about is that if we're using public clouds, we're deploying into someone else's infrastructure. So we don't have as full of control as we would in an on-premise world. So we have to remember that this is someone's data center. We don't have full control, and you need to take steps to make sure that things are still secure. Particularly when working in a distributed system, we can create security across nodes, because the nodes are constantly communicating with each other. They're sharing data, they're passing compute operations to each other, they're reporting the data back to the application. So we can set up TLS or SSL in between the nodes. We can also encrypt the disk. That does potentially introduce some additional performance bottlenecks if we're doing a lot of disk persistence. Some customers we see want to really control port access, so they lock down the firewall in their cloud instances, and found that's a pretty bad idea when you're working in a distributed system, because the nodes are constantly talking to each other. So maybe a way around that, or another way to think about it, is to set up like a VPN or a VPC, where all of the nodes in the cluster have the appropriate ports open so that they can communicate with each other. Data location. So one thing to think about as well is kind of where is your data stored? Is it entirely in the cloud, or are you working in a hybrid model where you still have some legacy or some business code that's still stored on your on-premise? And so for there, it's sort of a judgment call as to how you want to synchronize the data that's in your data grid in a cloud and that's stored back maybe in your on-premise databases. We've seen some customers do like batch jobs that's on a regular basis. We've seen others that have set up kind of regular jobs that will just do the diffs. But regardless of those two strategies, it does lead to a lot of bandwidth consumption. And so actually we've seen a few customers just go entirely cloud-based for their data storage. And that has been the best performance. And last is migration. So particularly if you're moving from on-prem and you want to store your data in cloud environment, there are a lot of different tools that you can use to help with that migration. And one of them actually is built into Ignite and GridGain, which is called the Data Center Replication Tools. And the way it works is pretty simple. You set up your data grid in a location. You set up the second location where you want your data to get either copied or pushed. And then we support either one-way or two-way copy. And it's fully automated. So it will go through each individual node in the cluster and push the data across and create the same representation over in the other data center. So it's a pretty easy way to get things started. And if you were doing this for pure migration, then you could go and close down your original data center and then it's been migrated to the new location. Or maybe you're doing it to maintain consistency across data center for something like high availability or something like that. It's a little bit different if you're working with like disaster recovery. In that case, you probably want to use like the snapshot feature of Ignite in order to have a local copy that you can then use the backup and restore features against. So that was the gist. So basically we've been working with customers in these different environments for 2 or 3 years now, and it can be kind of tricky to get started. And so, you know, there's definitely some value to deciding on a consistent set of tools when you're working with cloud environments, particularly around distributed systems. Memory sizing, there's a lot of different options out there, so knowing not to go too big is generally where a lot of our customers have found more success and saved money. Disk storage, there's many options out there. Custom images can make things more repeatable. In terms of performance, we got to think about kind of how you're reserving the instances and whether it's dedicated. For security, we've talked about how we can set up security between the nodes as well as around kind of port and firewall access. And then we also talked about kind of how we can look at migration. So any questions? All right. Thanks everyone. I will be available until the end.